So today we discuss about the uninformed state-based search. So now what does it mean? The uninformed state-based search, that means that type of algorithm don't exploit any knowledge from domain. That I can say about uninformed state search. So actually we know there are two types of state-based search problems. One is called planning problem. One is called planning problem and another is called configuration problem. Configuration problem. That means that these are the two type of state-based search problem. So in case of planning problem, here the solution is a path. Here the solution is a path and here the solution is a state. Solution is a state. যেমন আমরা করেছি like that wolf, goat, cabbage problem. We already did it. So in case of cabbage problem, what we find that here a wolf, goat and cabbage are there and you have to transport the trio to the opposite bank of the river. The conditions is given that wolf and goat cannot be left alone and goat and cabbage cannot be left alone. So these are the particular conditions and in that particular planning problem what we did actually, we did step by step calculation. That means what are the path is nothing but a solution. But in case configuration of a problem, we know like that n-queens problem. N-queens problem. So we know what do you mean by n-queens problem. There are different versions of the n-queens problem. Like that we know we have to place the queen. This is the, you say that this is 8 cross 4 cross 4 chessboard, or you can say board is there, and you have to use that like that. So what do you know in n-queens problem? You have to place the queen in each row. You have to place the queen in each row. That means each row will contain only one queen such that no queen will be placed in the, you can say, same column or in the same diagonal. That means if we want to place that queen at that particular position, that means in that particular position you don't, there is a restriction that you cannot place this next queen and that two positions. So you have to, there are only positions left, and when, since this queen is placed in that particular row, that means you cannot place any queen in that particular column and you cannot place the queen in that particular case also, because this queen is placed there. Since this queen is placed, so you cannot place it in, you can say, in particular diagonal also. So if you say that you place the queen in that particular case, that means you just see that all places are already been blocked. So in the next place there is no place to actually there is no place to actually put the queen. So you cannot, so that means you have to backtrack, you have to just remove this queen and then this and then this, and then you have to again try that queen at that particular, from that particular case. So what does it mean? That means that after some step there are particular state will be reached where the queen should be placed at particular their right places, satisfying all the constraint. So that is the in queens problem, but it is a configurations problem where the solutions is nothing but a state, but here the solutions is a path. So now, so what is meaning? That means for planning problem we modify the search node such that it can store entire path information. So that means for planning problem, for planning problem we modify the search node such that it can store entire path information, entire path information. If we say, if we take some example like that, what does it mean? That means if the graph is like that, say A, this is a B, C, say E, F, G, D, like that, a graph is like that. So now in case of planning problem, if we store the entire path such that how can we store? That means S, in that particular case you will go to B through S, so you can write like that BS. You can come to A through S, that means you can write AS. When we want to reach C, so you can reach through SA. If we coming through AS, then the path should be CAS, or you can coming through B also, so that depends on you how you draw the graph. So it is EAS, like that. The main thing is what I am trying to say, that in that particular case the nodes which have already visited, we make it closed by an encircle, and other nodes are in open. So when the goal node is reached, we just get the path from this node, as the node store the information of the whole path. So that means when we get the path from this node, that means when we reach the goal state, that means we will get the path from this node, because each node will store the information of the whole path. Where in case of configuration problem, search node is a list of two nodes. The search node is nothing but is a list of two nodes, like that, current and parent. So if this is S nil, this two node is BS, like that, this is AS. From that graph, this is a mother graph. So the thing is that it should be like that, CA, this is EA, say this is FE, this is G. So by using closed or open, all nodes are enclosed. So when the goal node is reached, we have to reconstruct the path. In that particular case, you have to reconstruct the path, because and take the goal node and go backwards to some source node. Then you will get the path, that how this path will be followed. So now if we consider search space, So this is the two different types of problems. So now we are considering search space. So say search space, what I am saying about that, you want to search this. That means if this is called a search space, if this is say source and this is goal node, then we know if we apply DFS, so what will happen? In case of DFS, the graph is this. What is graph? The graph is this one. The graph is this. This is the corresponding graph. Now if we apply DFS on that particular graph, what will happen? It will first visit this one, and no, it's not graph. If we take some different graph like that, uh, say we want to draw the graph like that, it will be better to represent that. Say the graph should be like that. Say this is the source node, and there are three nodes from S. One is AS. We are writing AS because it represents that A is the neighbor of S, B is also neighbor of S, and CS is also neighbor of S. Now from A there is some, you can say DA, that means D is a neighbor of A. This is the node A. E is also neighbor of that, and FA, and from D, that is G, that means neighbor of D, and say SD, and say this is ID. So now, so in this particular algorithm, so we can say that in this algo we are discussing about DFS. So in this algorithm we always find that newest node, that is newest node, is first explored. Newest node is first explored, and move the node in closed. Move the node in closed. You can say treat it as a closed as an array. So of course we are always searching for newest node. So this it so it approaches of greedy algorithm. So it is a greedy algorithm because in case of greedy আমরা কি জানি, ও সবচেয়ে বেশি যেটা প্রথমে প্রফিটেবল মনে হবে সেই নোডটাকে সিলেক্ট করছে। No, it is not about the selections of node, it's about anything. In case of greedy algorithm আমরা কি করি, সবচেয়ে যেটা আমার বেনিফিশিয়াল লাগবে at that particular moment we are selecting that, not depending on the global view. We are only concentrating on the local view. So of course that also we find that this algorithm also deepest node first. We find that the algorithm follow this algorithm depth first search. This algorithm actually follows deepest node first. So what does it mean, deepest node first? That means initially what will happen, it will first actually select this one, then it is goes to closed, and then this one, then this one, and then this one. If it reaches goal node, then the algorithm is stopped, and this particular open where we are just selecting particular node, that open is behaving as a stack. So the thing is, so the search space for DFS, it looks like that. So if we say about the search space of DFS that looks like, if this is the corresponding search space, if this is a source node, and if this is a goal node, we are just expanding our node depending on our algorithm, not just seeing the goal node. That's why that type of searching is known as blind search. So it will be expanded like that. If these are the corresponding node, it will be first explore this one, say, then it's explore like that. So it goes on like that. So here the algo goes deeper without notices. So here the algo goes deeper. It goes deeper without notices the goal node, without notices the goal node. So this type of, so these are called blind search. These are called blind search algo, or you can say uninformed search. So if the search space is infinite, it may be possible the search space is infinite, that it may be possible that your DFL will not reach to the goal node. That means it goes deeper and deeper and deeper and deeper. And if the search space, this search space is infinite, then it may be possible that your DFS will never reach to the goal node. So if this search space, if the search space is infinite, if the search space is infinite, so it may be possible, it may be possible that DFS will never reaches the goal node. It will never reaches the goal node. Now how the BFS will occur? BFS will do. Now if we see the same graph, that means the graph is, say, S nil, and there are three nodes from S, AS, BS and CS. From A there is DA, EA and FA, and there is GD, SD and ID. So in that algorithm we always find the oldest node. Here we always find the oldest node. That's why we are using SAC. Oldest node means যেটা প্রথমে ঢুকেছে সেটা সবচেয়ে ওল্ডেস্ট, সেই প্রথমে বের হবে। আর স্ট্যাকের কনসেপ্টটা কি ছিল? নিউয়েস্ট নোডস। নিউয়েস্ট মানে যেটা লাস্টে ঢুকেছে সেটা প্রথমে বের হচ্ছে। দ্যাটস ওয়াই দ্য কনসেপ্ট অফ স্ট্যাক ইজ ইউজড। হিয়ার দ্য কনসেপ্ট অফ কিউ ইজ ইউজড বিকজ you always find the oldest node that are first explored, and then it move the node to closed, so here this particular open is behaving like a queue, and in the previous class we just see the example and see the algorithm what is open and closed. So in that particular case it will be explored like that. First this node is explored, then this, then this, then this. So it will be explored like that, level wise it will be explored like that. Okay, so the search space, so how the search space looks? So search space looks like, you can say, if this is the search space, if this is the source node, if this is the goal node, then the search space is explored like that. Then if you select this particular node, it will be explored like that. So it will be moving like that in a circular, it will be explode like that. If it will be explode like that, how much time it will take? It doesn't matter. If the search space is infinite, then also at some time it will reaches the goal node. So in DFS we go away from the source node, where in BFS we move close to the source node. So in BFS, if the search space is infinite, in spite of that we can find the goal node. So BFS gives the optimal path in respect of number of nodes, and if the weight of the graph are same, you can say it will give optimal cost. So what I am saying that in DFS we go away from source node, where for BFS we move close to the source. So in BFS, if the search space is infinite, if the search space is infinite, in spite of that, we can find the goal node. So BFS, you can say that, gives the optimal path in respect of number of nodes, and if weight or cost, whatever be the weight of the graph, are same, then it gives optimal cost. So that is the BFS and DFS, as we already explored in the previous class, that how it behaving like the open or close like that. If you just forget it, I am just giving one example. That means if say we are in case of DFS like that, if S, this is M1, say this is M2, this is M3, like that, this is M4, this is M5, this is R, and say this is M6, and say it should be like that, it is given like that. So now what I am saying, that open, and if it is a close like that, if S is put in open, first S, then from S the neighbor is M1 and M2, and when we just remove M1, so in that case open is behaving like a stack, and we are just put successor on the top of the open, except those already in close. That is a simple concept. If M1, so from M1 the neighbor is M4 and M3, so you just first put S in closed, and from S M1 and M2 as explored. Since this is a stack, so you can say like that, first M2 then M1, then top of the stack is removed and it is put into M1. And what we have to say, that in that particular stack we just put the neighbor of M1. M1 is M3 and M4. You can put in any order. So you can put M4 and then M3. So it should be like that: M3, M4 and M2. And since it is a tag, then M3 will be popped out and it is closed. You can put it in closed. So from M3 there is M4 and M5. So you can like that M2 is there, M4, and from M3 this is M4 and M5. So we can put like that M5 and M4. So it should be M4, M5. It is again M4, M2 like that. So you just remove it from M4 and S. It is M1, M3 and M4. So M4 will be popped out, and from M4 this is a M6 and R. R is the gold node. So this is R and M6. This is M5. This is M4. This is M2. And you can say you can put out R, and that should be M1, M3. This is M4 and R. So if we reach the goal node, you can stop your algorithm. So in that particular case, you can say that if we just backtrack that from S, there is, you first explore M1, then you explore M3, then you explore M4, then you explore R. So you can say that is the corresponding path. You can say you can follow this path, and that is the algorithm of, you can say, BFS. So here the open is closed is looking like that. In case of, if we just do the same thing for BFS, then instead of using like a stack, you are using this open behaving like an queue. So that is the basically the difference between BFS and DFS. Now the thing, if we just analyze the performance of BFS and DFS, then what I am saying that in case of, if we just consider the performance analysis, so you can say that we are just exploring the time complexity. Say this is the corresponding BFS and this is the BFS. So first thing we are discussing about the time complexity. So say let the branching factor is constant, that is we taken as an assumption. So we know that, say for in-Queen's problems, let for in-Queen problem, what I am saying that the search tree, if we consider search tree, it will be like that, that if D, this is called depth, that means is D queen problem in that, so there is a depth D. So at that last level there are, you know that B to the power D nodes are available if this consider and the last node. So let the branching factor, let branching factor is B, and of course it is taken as a constant. If this is taken as a constant, and depth be D, and if we consider depth be D. So now at the last layer, so we know that at the last layer there are B to the power D nodes. If you know that branching factor, that means, what do you mean by branching factor? That means is the corresponding branching factor. That means if branching factor is constant like that, so this is also, there are 4 and this is also 4. So if this depth is 3, branching factor is 1, 2, 3, 4, then of course the number of nodes at the last level is b to the power d. So branching factor is 4, that means 4 to the power 3, that means the total number of nodes 4 into 4 into 4. So of course 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 like that. If it is starting from 0 also, so depth is 2, so 2 to the power 2, that means it will come out 16. So this is the thing that I want to say, that at last layer there are b to the power d nodes. So and all internal nodes except last layer is, and if we consider all internal nodes except last layer, you can say that should be b to the power d minus 1, b minus 1, and for large b we can write like that, b to the power d b minus 1 can be written like that, b to the power d by b minus 1. That means at the last layer it will contain b to the power d, and all internal layers will contain only this amount of, you can say, number of nodes. So the thing is that, so the dth layer contains more node. That is the important observation, that dth layer contain more nodes compared to all internal nodes of the tree. So let the goal can be anywhere in the last node. So it may be possible let the goal can be anywhere in the last node. So in this, the goal node can be found only at the depth d, because we know that it will be exploring like that, it will go deeper and deeper. So if we want to find the, you can say, the average case time complexity, say average case time complexity, then say we are exploring the node like that, say this is point A, we can say this is point B. So if the goal node, then after d plus 1 inspections we found it, or at B position it will take some other time. That means it may be that the goal node at A, it will be found after d plus 1 inspections. It may be possible that we are going deeper and deeper, and at d plus 1 level you will find the goal node. But it may be possible, that means this is depth wise, then again it will be back, again this will be back, again this will be, it may be found that your goal node will be at some point this. So if what I am saying, that goal node can be found after d plus 1 inspections, or it will take b to the power d plus 1 minus, you can say, minus 1 by b minus 1 inspections. That been all internal nodes. So if we just approximately calculate the average case, then it will found that plus b to the power d plus 1 minus 1 by b minus 1 by 2. So it's approximately b to the power d is the corresponding, you can say, time complexity for searching DFS. So now if we consider BFS, and the time complexity, then if we consider BFS and the corresponding time complexity, what I am saying that in Oates case, suppose that our solution is a depth T. So in Oates case, what I am saying that suppose that our solution is at depth D. We explain all nodes and we expand all nodes, but the last node at level D. So hence total number of generated nodes 1 plus b square. You were, because in DFS you are just searching like that, but in BFS you are searching all level by level, first this level, then this level, then this level, like first this one, then this level, then this level, then this level, like this. So all number of nodes is near about all of b to the power d. So actually if you slightly analyze the complexity of BFS and DFS, if we say that time complexity of BFS by time complexity of DFS is near about, you can say, b plus 1 by d. So BFS takes a, you can say, little bit larger time compared to DFS, but not much more, you can say, that we can analyze. That is the first performance analysis, that analyzation, that is the time complexity. Now if we consider about the completeness, the second parameter that we consider, that is called, you can say, completeness. So if we consider completeness, we already know that if the search space is infinite, that it may be possible that DFS will not found the solution, so it is not complete. So what I am saying that we know already that if this is the search space, if this is the source node, if this is the goal node, that it will be exploring the nodes like that, DFS. So it may be possible that if the search space is infinite, then it may be possible that we cannot reach the goal node, so it is not complete. But what I am saying that in case of BFS, if this is it is a source node and it is a goal node, then it will be explore the node like that. That means it will be exploring like that, in that particular fashion. So if the search space is infinite, then also you can find a goal node. So if it visit, so what it visit all levels given that D factor is finite. So in sum D it will find a solution. It will find a solution. So you can say complete. So now the quality of solutions. So you can say, if we discuss the quality of solutions, the next parameter is quality of solution. Then what we know that the number of nodes in path, that is which one is shorter, like that you can say if this is, say this is C, this is B, this is A, this is D, say this is A, and say this is E, this is G, H, and say this is F, like that. So number of nodes in the path, like that, if we goes like that, first A, then C, then D, then F, like that. So the path is nothing but source C, then D, then F, then G, like that. So this is a path, but in BFS we are searching all the nodes level by level. So BFS always find the shortest path, that is always guarantees shortest path. যেমন ধরো নেটওয়ার্কিং যখন পড়েছো বা পড়বে, আমরা কি জানি যখন রাউটারের ক্ষেত্রে আমরা অ্যাকচুয়ালি শর্টেস্ট পাথ বার করতে চাই, যদি ডিএফএস চালাই তাহলে কি করে অল পসিবল পাথও সার্চ করবে এবং তার মধ্যে থেকে শর্টেস্ট পাথটা আমরা বার করে নিই। তার মানে অপটিমালিটির রেসপেক্টে দ্যাট স্কোর হেভিলি ইন রেসপেক্ট অফ অপটিমালিটি, বিকজ ই অলওয়েজ স্কোরস heavily in respect of optimality. So that is, you can say, about the BFS. But in case of DFS we may not be find the, you can say, optimal path. So that's why in respect of optimality BFS will course heavily compared to the DFS. So now the last is size of open. Size of open. This is another parameter. So, or you can say space complexity in another term. So we know we are exploring if this is the corresponding nodes. So we are flush in case of exploring this, then this, then this, then this, like that. So but at DFS at each level only constant number of nodes are added. So we know that at DFS only constant amount of, because it is going depthwise, so constant number of nodes are added to open. So nodes at, so nodes at that open increases linearly, So you can say b minus 1 number of nodes are added each edge level. So you can the phase complexity like that. But if we consider if we consider BFS, then nodes at closed, it will be like that. This is the nodes are closed at each level because it is searching like level wise. So that is the number of nodes at open. So in BFS, as we see that the nodes in open is half from B to the power D level and half from B to the power D plus 1 level, because it will be at, say, this was the B to the power D level, and in the next level, that is a B to the power D plus 1 level. So that number that can be in open nodes, in open maximum, in the worst case you can say. So what I am saying, that in BFS the nodes in open is half from this level. This is a B to the power D level, from B to the power level, and half from B to the power D plus 1. So that are which are in open. So at each level the number of nodes increases exponentially with the branching factor, that is a linearly increases. Here the number of nodes increases exponentially with branching factor, with branching factor. So in the next step, what I am thinking about, so there are some, you can say, the positive side of DFS and there are some positive side of BFS. So can we devise an algorithm which uses DFS open list because it is linearly added and which is constant, and BFS time complexity or completeness, because BFS is better in respect of time complexity and completeness. So the next step, that what I am thinking, that can we devise an algorithm which uses DFS open list because space complexity is linear in case of DFS, and because it is constant, and BFS is better in respect of time complexity and completeness. Then there is an algorithm which is called depth limited search, or somewhere this is named as bounded search, and after that there is DFID, depth bound DFS. So these are the algorithm that try to, actually you can say, use the benefits of both algorithms.